GMMs, Gaussian mixture models. Okay. So I assume that all of you are familiar with what do I mean by a mixture of Gaussians. Okay. If not, I urge you to go into the book, which is Pattern Recognition and Machine Learning by Christopher Bishop, especially to the chapter 9, wherein which he deals with mixture models and EM, wherein which he has explained in depth how the algorithm actually works. Okay, it's a very important read. Now I assume that all of you please look into it. Now the derivation that we shall be doing will be from the same text, and the notations that we shall be using will also be from the same text. Okay, now let's define the problem first. Now we know that in this case, GMMs is a special case of latent variable models, now wherein which your latent variable is discrete. Okay, that is the assumption that we are making. It's a Z. Your latent will be a discrete distribution. Okay, so now let's take my X is X1 till Xn, which is sampled IID from the data distribution Vx. Okay. And I'm assuming that I'll take any xi that is in the dimension Rd. Okay, and the latent that we are considering Z is a discrete random variable which take Z belongs to, it will take values from Z1 till Zk. Okay, and this is what is our assumption. So, and then for any given xi, any point xi, now it is combination of some Gaussian. Now how do you get it? It's summing up over z p theta of xi and z, which is nothing but p theta of z, p theta of xi given z. Now if you consider that there are k of these, z equals 1 to k, now p theta of z equals to, okay, I should have given, this is k equals 1 to capital K. Okay, z is equal to k. Now p theta of xi given z equals to k, and this will be nothing but some mixing factor, which is summation k equals 1 to capital K alpha k normal xi parameterized by mu k sigma k. Okay, now this is for one specific data point. Now how do you compute the conditional one, that is z given x? Okay, so now let's take that. Now probability of z belongs to a group k given xi. If that is the case, now we can write it as xi comma zk divided by probability of xi. Okay, Now this, by using the Bayes rule, I can write it as probability of Zk and probability of Xi given Zk divided by probability of Xi. Now I know these substitutions. Now this is alpha k, this is normal, Xi, which is parameterized by mu k and the covariance sigma k, divided by summation j equals 1 to capital K alpha j n of Xi mu j sigma j. Okay, so now we call it as for the ith point. Now what is the responsibility that kth Gaussian will take? Okay, this is one important value that now we should be computing. Okay, so now let's proceed similarly. Okay, so now what is the final aim? The final aim is to maximize the log likelihood, right? Now what is log likelihood? Let's consider that log likelihood. Now first, that is p of x equals product of I is equal to 1 to n probability of individual xi. So then if I take in the log scale, this is log of p of x is log of the product I is equal to 1 to n p of xi. Now we know the logarithmic rules. Now this will be I is equal to 1 to n log of p of xi. Now we know this value already, not needed for us. Okay, you know these values. Now this will be summation I is equal to 1 to n. Now this is log of summation j equals 1 to capital K alpha j n of xi, which is parameterized by mu j and sigma j. Okay, now this will be your log likelihood. Now what does the EM algorithm say? Now finally let's recap the statements of EM algorithm. Now the EM algorithm has two steps. Now one is the E step, the expectation step. Now it's an iterative algorithm. Now with theta at the stamp t, now I keep it as a constant. Okay, what I'll do, I'll get the t plus 1, which is the argmax of j of q. This is my E step. Now what is this? Now this is nothing but p of z given x. That means that in each step, you will be finding this value by keeping this mixing coefficient mu k and sigma k as constant for all the case. Okay, for all the mixtures, you will be finding it by keeping the mixing coefficients and the parameters as constant. Okay, so now then in m step, what you will do, now you will take that with the obtained t plus 1 as constant. Now what you will do, you will get theta star. In that specific case, you will get theta star of argmax of theta of t plus 1. Now that means that, now what do you do? By keeping these responsibility coefficients as constant. Now you will find this alpha k, mu k, and sigma k. This is what you will be doing in the uh, M step. Okay. Now E step is pretty much clear. Okay. Now you will be computing these. Okay. So now let's go to the M step now, which is important to us. Okay. Now in the M step, now you have three. You need to your theta. Okay. Your theta is a set which is having your alpha j equals 1 to k, and your mu's j equals 1 to k, and your sigma is also j equals 1 to k. Now you need to compute these parameters. Okay. So now on alphas, now there is a constraint. Now it says that now if you take the summation of all these alpha j's, now you have to get one. Okay. Now, there is no such constraint on these parameters. Okay. So now whenever we are trying to optimize, now we need to do a constraint optimization. Okay. Now in this case, now we need to do a, you cannot get any values of alpha. Now, there is certain constraint that needs to be taken care. We need to do a constraint optimization. Okay. It is done. We will look into it. Now to do so, now we need something from the optimization theory, which is we need something called as a Lagrange multiplier. Okay. We need a Lagrange multiplier. Now when you add this Lagrange multiplier, now your overall optimization function now will be like this alpha of this j equals 1 to k alpha j minus 1. Now this will be your new optimization function. Now let's call this as L. Okay. Now this will be your new optimization function. Now how does this optimization function look like? Now this will be summation I equals to 1 to n log of summation j is equal to 1 to k alpha j xi parameterized by mu j and sigma j. This is your regular log likelihood. Now, in addition to that, you need a Lagrange multiplier. Okay. Okay. So now this is the function. This is the optimization function that we want to do it. We want to maximize this particular constraint. Now, how do we do it? Now, the idea is straightforward. You take the derivative and then equate it to 0. Okay. Now we need to do it for three set of parameters. Now one for mu, one for sigma, and another for alpha. Now let's start from a simple one, alpha. Okay. Now let's give this equation some name. Let's call it as A. Okay. So now differentiate A with respect to alpha j. Okay. And equate to 0 and equate to 0. Okay. So now that is equal to 0. So now you want to take the derivative of this. Now there is a summation you get inside. Derivative of log of something, that is 1 over that specific quantity, and then the derivative of that quantity. Now you have a summation you get in alpha j into this. Okay. Now I'm assuming that you guys are comfortable with the rules of differentiation. Now this will be summation I equals 1 to n 1 into xi mu j sigma j divided by summation j equals 1 to k alpha j n of xi mu j sigma j plus lambda equal to 0. Okay. This only one term will be having alpha j, the remaining terms will be 0. Wherever is alpha j, you will get this lambda. Okay. And then this is a chain rule which you can apply. Now what I will do is now the problem is multiply by alpha j. Okay. Then both sides I equals 1 to n alpha j n of xi, which is parameters by mu j and sigma j, divided by the summation j equals 1 to k xi mu j sigma j plus equals to 0. Does this term look, okay, not this term, does this term look familiar? Have we looked at this term any time earlier? If you go back, this is the responsibility. Okay, normally this is called as responsibility. Now this will be summation I equals 1 to n ij plus equals to 0. So then alpha j, if you rearrange the terms, is equal to 1 to n minus lambda. Okay. Now this is rewritten as nk divided by n. Okay. Now this is substituted by nk. This lambda is given as n. Now this is how you get the first terms in the case. Okay. Now you got the mixing coefficients now. Now the remaining things needs to be looked into. Now you need to get mu k and sigma k. So now let's do that. One part is done. Now to get mu k, you should follow the similar thing. Now differentiate with respect to mu j and equate to 0. What? Equation A. Let's go back to equation A. This term is independent of mu j, so no problem. Again, now this will be like log of this. Now this is 1 over this term will come. Now you want to differentiate this. Now you get, okay, this term into the derivative of this. Okay, I will be doing one after another. And then the normal distribution, you know the equation. Now 1 over 2 pi to the power of half, 1 over sigmas, all those things, you know the equation, right? Okay, and then even for the multivariate case, now you know how to do it. Okay, I'll be just be going ahead and writing the equations. Mu j of L equal to 0, then I get minus of I is equal to 1 to n alpha j n of xi mu j sigma j divided by summation j is equal to 1 to capital K alpha j into n of xi mu j sigma j into, now if you differentiate the exponential terms, you get sigma k xi minus mu k equal to 0. Now we know this term already. Now this will be I is equal to 1 to n ij sigma k xi minus mu k equal to 0. So now you should remember that this is a matrix. Okay. Now this is a square matrix. Okay. Preferably it will be a diagonally dominant matrix. Therefore, we can assume that the inverse exists, and then we can multiply by the inverse of this matrix. Okay. This is a scalar anyhow. Okay. So now you can multiply by the inverse of this. Multiply both the sides by, oh sorry, it has to be j. Okay. There is an indexing mistake. It has to be mu j xi. Sorry, this has to be sigma j. This is mu j. Okay. Multiply by inverse. Now you get summation I is equal to 1 to n. Then you multiply this ij xi minus summation I is equal to 1 to n mu j. Okay. Now this is equal to 0. Okay. Now this is independent of I. So now you can take it as nk, but this is not independent of I. I is there here. So now this will be mu j equals 1 over nj. Okay. Summation I is equal to 1 to n ij xi. Okay. Now this will be the value of mu j. Okay. So now similarly, now on a similar steps, I'll not be going ahead with how do you calculate the values of sigma j, but you have to follow the similar steps. Now differentiate with respect to sigma j and follow the similar steps. You get sigma k, okay, sigma j equals 1 over nj summation I is equal to 1 to n xi minus mu j into xi minus mu j transpose. Okay, now this will be the value that you get. This completes our derivation. Now how will your the steps looks like? Okay, how does your EM steps look like? I'm directly quoting this from page 439 of Bishop. Okay, now how do you do this? How do you code this? Okay, I'll give the steps. Now let's see. So now, given the Gaussian mixtures, the goal is to maximize the likelihood function with respect to the parameter, okay, to get mean, covariances, and the mixing coefficients. Now first, let's look at the algorithm. Step 1, okay, initialize mu k, sigma k, and alpha k, okay, and compute the initial log likelihood values. Okay, and the second step is the E step, now which is evaluating the responsibilities with current parameters, now you get ik. Now the third step is M step. Now this is re-estimate the parameters using the current responsibilities. Okay. And with that, you calculate new values of mu k, sigma k, and alpha k. You get new values. Okay. And then the fourth step is evaluate log likelihood. Okay. Now, if not convergent, okay, if you are not satisfied with the convergence, if the convergence is not satisfied, return to step 2. Okay, this is your overall iterative algorithm for EM for Gaussian mixtures. Okay, I hope this derivation gave you a very nice mathematical foundations on how to handle the EM. So we will stop at this point, and then we will meet in the next tutorials with implementations of variational autoencoders. Thank you.